Is the following statement true that for all integers a, b, and c, if a divides b and b divides c, then a divides c? Well, I can see this is true, but people oftentimes don't, so let's go ahead and do what people that don't see this do, and that's think of examples. Let's use the easiest example I always like to use, and that's going to be 2 divides 4. We know that this is true from all of our previous videos. And then since we're looking at a divides b, we then want to take what's on the right-hand side and see if that divides something. So we're going to see 4 and ask, well, what does 4 divide? 4 divides 8, right? So we're asking, these are true. Is it then true that if you take the left number here and the right-hand number here, that it's going to be true that 2 divides 8? Well, let's think about it, right? What does it mean for 2 to divide 4? It means 4 is a multiple of 2, which means 4 can be written as 2 times x. What does it mean for 4 to divide 8? Well, that means 8 is a multiple of 4, and that means 8 can be written as 4 times y. The important thing to note here is x and y must be integers in order for the numbers on the left to divide the numbers on the right. And in this case, we find that they're both equal to 2. This does not have to be the case. I could have chosen, let's say, 16, and then I would have written 16 here, and then y would have been equal to 4, and x would have been equal to 2. So they don't have to be the same. They can be different very clearly here. Well, then we ask ourselves, let's also do 2 divides 16 for the sake of example. Well, then is this going to be true? Well, yes, because you can say that 8 is equal to a multiple of 2, because 8 can be written as 2 times k. And if we rearrange for k here, we find k has to be 4, and that's in fact an integer, so it's true that 2 divides 8. Same thing with 16. We're going to ask ourselves, well, this means that 16 can be written as 2 times m, and m has to be an integer, so if we rearrange for m, it must be an integer, and we find that m is equal to 8 when you rearrange for it, and that is an integer. So it's looking like for 2, this is going to be true. Let's quickly just verify this for some of the negative numbers. So if we take something, for example, like, let's jump around between negative and positives, right? Let's take something like, what can we use? I'm thinking, let's try 3 and negative 6. And then let's take negative 6 and let's take negative 6, what am I want to do here? 12. So we're jumping from positive to negative and then back from negative to positive. So let's make sure this is true. So negative 6 should be a multiple of 3 for this to be true, and that is in fact true. Because if we write this as negative 6 is equal to 3 times k has to be an integer for this to be true, and when we rearrange for k, we find k is equal to negative 2. And negative 2 is an integer. Same thing here, we're going to ask ourselves, okay, well then is it true that 12 can be written as negative 6 times z, where z must be an integer? And that's true because when we rearrange for z, we find z is equal to 2. Fantastic, negative 2 and 2 are both integers. So then our final question is going to be, okay, if we take the left number over here, the right number over here, is it going to be true that 3 divides 12? And I think most of you could see that that's true, because 12 is a multiple of 3, because 12 can be written as 3 times j, where j must still be an integer, and the integer here that j must be is going to be 4. So it's looking like for negatives and positives, it doesn't seem to matter. This statement is looking like it's true. I can't really think of any counterexamples, apart from the ones where it's 0, but remember, a cannot be equal to 0 unless a and b are equal to 0. Maybe I will do a proof where I prove that that is the only time that that is true, but that's not the subject of the video. So looking like this statement is true, let's go ahead and try and prove it. So this is a for all statement, and how do we prove all of our for all statements? Well, we start with the word let, and what do we say? We let a, b, and c be integers, right? We create some variables a, b, and c. Then we need to suppose this part of the statement over here. We need to suppose our if, or as it's called in math, the p statement. So we say such that, or we can just put a full stop here, and then we can say suppose A divides B and B divides C. Fantastic. Now we want to mathematically turn these into actual equations we can use to use algebra. So we say then, comma, B must be equal to A times, man, I always struggle with coming up with letters for these. Let's use gamma. Let's use some other letters from other alphabets. And this over here means C must be equal to B times, let's use alpha. And of course, now that we've introduced to the reader some new letters, we have to clarify what those letters are. We say where gamma and alpha are going to be integers. Fantastic. Next, we want to show that it is in fact true. Actually, I'm going to change this from alpha. Since we have an A in here, it's going to be a little confusing. So instead, I'm going to use beta. Yeah, that's going to look a little nicer. Okay. We've supposed everything we can, and we've better defined everything we can. So all that's left is to check that for this to be true, it must be that C is a multiple of A. And what does it mean for C to be a multiple of A? It means C is equal to A multiplied by some bracket or some one variable, whatever it might be. Whatever A is multiplied by must be some integer. So let's go ahead and try that. Well, we have C over here, and we know what B is. So maybe what we can do is we can take this over here and just plug it into our B right here, right? So let's go ahead and give that a shot. So we can say in our sentence, therefore, C is going to be equal to B times beta, which is going to equal to A times gamma times beta, right? We just replaced our B here, which is going to equal to, we can simply just take away the brackets or place the brackets on our Greek letters here. We can say it's the same as saying A times gamma times beta. And there we go. We've now shown that this is in fact, C can be written as a multiple of A because C can be written as A multiplied by something in brackets, whether they're square or round, it does not matter. And whatever's inside of these brackets is an integer because you have to recognize that because gamma and beta are integers, any two integers, the product of them is still going to be an integer. So we say, so gamma beta is an integer. Don't put a comma there. This is one thing. Alpha times beta, sorry, gamma times beta is one thing. You don't put a comma because then you're just going to restate what we have up here as two separate things. No, we're saying this one thing together is an integer. So we can say, in conclusion, C is equal to alpha, or A times gamma times beta. So C is a multiple of A. So it's true that A divides C. This is called the transitivity of divisibility because we're transferring, right? We're going A goes to B, and then B goes to B, and then B goes to C. This is kind of what transitivity is hinting at here. So we've just proven that because they share this bridge B, it's true that A divides C.